Now it's time for the address of Professor Leonard Kleinrock, our General Chair. So before giving him the floor, I'm going to read out, I'm sure that all of you know about Leonard, but I'm going to read out a short bio of Leonard, just to give you an idea for the few that might not be aware of the stature of the person who is going to address you. So, Professor Leonard Kleinrock is Distinguished Professor of Computer Science at UCLA. He is considered the father of the Internet, having developed the mathematical theory of packet networks, the technology underpinning the Internet as an MIT graduate student in 1962. His UCLA host computer became the first node of the Internet in September 1969, from which he directed the transmission of the first Internet message. Kleinrock received the 2007 National Medal of Science, the highest honor for achievement in science bestowed by the President of the United States. Leonard Kleinrock received his PhD from MIT in 1963. He has served as Professor of Computer Science at UCLA since then, and was department chairman from 91 to 95. He received a bachelor degree from City College, New York in 57 and a master's degree from MIT in 59. He has received 8 honorary degrees, has published over 250 papers, authored 6 books, and he has supervised the research of 50 PhD students. Dr. Kleinrock is a member of the National Academy of Engineering, the American Academy of Arts and Sciences, is an IEEE Fellow, an ACM Fellow, an Informs Fellow, an IAC Fellow, and an inaugural member of the Internet Hall of Fame, a Guggenheim Fellow, and an eminent member of Eta Kappa Nu. Among his many honors, he is the recipient of the National Medal of Science, the Erickson Prize, the NAE Draper Prize, the Marconi Prize, the Dan David Prize, the Okawa Prize, the BBVA Frontiers of Knowledge Award, the Orsa Lanchester Prize, the ACM Sigma Award, the SIGMOBILE Outstanding Contribution Award, the IEEE Leonard G. Abraham Prize Paper Award, the IEEE Harry M. Good Award, the IEEE Alexander Graham Bell Medal, the UCLA Medal, and more. So it's my real pleasure and honor to introduce Professor Leonard Kleinrock.
Okay, wonderful. Well, thank you very much, Marco. That was an extended bio. We can ignore that, even though it took some time for my presentation. It's been a very interesting meeting so far, and I'd like to address this young, budding group of researchers and engineers that we've been hearing about and heard about their papers. The title is an interesting title, On the Shoulders of Giants. I'm going to use that as a clue regarding the material I present. I want to talk about some of where the technology has come from that we're all talking about, talk about the culture in which that environment has been implemented and what's happened to the systems we built and how they're being used, and finally talk a little bit about the a tiny bit of technology which I can't not discuss at some point. So in many ways, this meeting is a tribute to Mario Gerla, whom we dearly miss. And I, for one, can feel his presence here at the moment. So whereas we, just a moment, I'm having trouble advancing. We'll try this way. So there's the Mario we all know. We've seen his picture on a number of the advertisements for this conference. Brilliant young man whom I've known for 50 years. But I'd like to show you some other scenes in Mario's life that are reflective. For example, that's the young Mario. One of the pictures as a young man. Here he is again in a green sweater at a retreat of our department, not far from Los Angeles. There he is again, ready to do his usual hiking, packing, swimming, jumping, running, leaving us all behind in the dust. And here he is, having just come back from an energetic event. Now here Mario's having some fun. I'll pass this quickly because I want to point out early Mario with Maggie, whom you heard a few minutes ago. There's Mario at my home in 1977. And there he is with Maggie next to him, chatting with me. And a beautiful picture of the two of them before they got married. They got married about a year later. And not long after that, Marisa and Chris were on their way. Mario has many personalities. For example, here he is, his arm around a beautiful young woman. Here's the Mario I know so well, the teacher, the enthusiastic, the energetic, and the brilliant young man, always in a pose of that sort as he lectured to all of us. Here Mario seems to be explaining the complexities of networking to Vin Cerf. I love this picture. Here Mario, the cook, is enjoying his own food in a really gluttonous and wonderful way. Now Mario was able to get formal as well. Here you see Mario dressed up in a formal tux, very conservative and quiet. Here we are with a number of my former students, a number of whom are on this call today, but he's already beginning to smile. He can't quite contain his energy and his exuberance. And now he's beginning to horse around and mess around and trying to break us up. And sure enough, he's broken us all up with his enormous energy, laughter, and charm. So it's a tribute to Mario. That's the Mario we know. And Mario, you're here, and we can feel your presence as we go through this. Now, here we're at MedComNet, beautiful arena that we could have gone to, but the pandemic took care of that. But that's being Mario's birthplace. And a freshwater, I didn't realize it was the first freshwater event we were going to attend. If you look at the program which you have, you can see the people who basically made all this happen. It's a long list of hardworking, dedicated people, a number of whom you've talked about. But let's go back to the first of the MedComNet meetings, 2002. It took place in Sardinia, Italy. We had a wonderful conference there. And the call for papers looked like this. They were going to explore ad hoc wireless networks. We're going to have a variety of topics, including nomadic access to the internet. That was a hot topic in those days. And bringing together researchers from all over the world, where? To the shores of the Mediterranean. And indeed, this group has accomplished that. Now, to get back from this, it's always a trick. Oh, there we go. This was the final program and a list of many of the organizers. Let's see. This becomes a challenge, by the way, with GoToMeeting. The program itself looked like this. And the first thing you notice is we began with cocktails and then a dinner. And then there was some technology taking place. And it wasn't long after that we had a lunch and a swimming break. This, by the way, was in Bodrum. So then we go on some more sessions, and then a dinner again. And I was the fact speaker. I'm going to show you a little bit about that later. And not to be overburdened, another swimming break with a lunch. So that was the nature of what was going on. Deep technology, great camaraderie, and great festivities. Now, as a group, of engineers and researchers and mathematicians, I'd like to go through some of those giants who have given us this wealth, this of golden information over centuries. We can begin with the whole field of electricity and magnetism, where much of what we do comes from, starting in 1735 with Cookson and going through Maxwell and Gauss and Faraday and Hertz, Kirchhoff. If you haven't read the original works by many of these people, you really should do it. I mean, if you go to a book by Faraday, you can hear the way in which he physically and intellectually understood the phenomena of electricity and magnetism. It was in his bones. He had an intuition as well as an experimental and a mathematical strength, as did many of these people. The telegraph started in 1831, finally being implemented by Morse in 1844. Again, good theory behind an important experimental and eventually deployed system. Telephony, all these people started from 1840, finally to Bell in 1876. If you look at radio, a topic with which we're all familiar and we spend a lot of our research time on, here is a timeline from many of the contributors, beginning with Maxwell, going all the way through Hughes, Hertz, Tesla, Bose, Popov, Marconi. Basically, this was an international effort, as were many of the efforts I just described. These are the people who laid the foundation and explained to us exactly what we need to deal with. Now, there's also the mathematics behind our research, the queuing theory, the performance evaluation, etc. And of course, none other than A.K. Erlang, when he actually, as an engineer, as a telephone engineer in the Copenhagen Telephone Company, he was also a mathematician, took his intuition as an engineer and his mathematical brilliance as a theoretician and put them together to form the first models. And in fact, as we know, created some of the early important formulas of queuing theory. As soon as that work was done, queuing theory was in the domain of telephone engineering applications. That's where the effort was placed. It was recognized by Feller that what Erlang was talking about was a birthday process. And so the mathematician stepped into the picture, put the theory on a firmer mathematical basis, and an era of mathematicians began to dominate the growth of queuing theory until World War II period, and industrial applications came to the fore, operations research was born, and communication theory was grandly developed by Claude Shannon, as we know, and the others around him at Bell Labs. So again, we're moving from an engineer, strong mathematics, a combination in applications and theory. And finally, I had the opportunity to initiate the use of this theory in the data networks and the computer systems that we have today, in which case it's grown and taken root. And the papers we're talking about here for the last 60 years have been based on elaborating and extending the theory that we've all been contributing to. So an interesting comment about the early mathematical theory of packet networks. The comment is, the theory was already developed before the early internet was implemented. So this is an example of a deployed system whose mathematical structure was well understood. It wasn't complete, but there was theory, anticipation, design built in long before it was deployed, as opposed to many other systems which are just thrown out there, and then people begin to scratch their head and say, well, how does this work and why is it working this way? Now, if you look at some of the early internet visionaries, people who were anticipating the internet that eventually came out, certainly Nikola Tesla stands out. And I'm going to show you a quote he made in 1908. Basically, he said that it'll be possible for a businessman in New York to instantaneously send information to his colleague in London using a device no larger than a watch to send transmission any other place instantly, inexpensively. And what were they going to send? Photographs, pictures, characters, drawings, print, text. This sounds like the internet described in 1908. It was a vision. It didn't have video because there was no video at the time. So here we see an early vision as to what a thing like the internet could become. But of course, we had to wait for the technology to catch up and the need. Others along the way, Wells, Bush, Shannon, Licklider, given the dates there, all had commentary about things that now exist in our internet and some of the underlying technology behind it. Now, if we fast forward to the deployment of the internet and look at the people who contributed to it without going into their detailed contributions, talking about on the shoulders of giants again, here are some of the early pioneers. Here are the implementers. You should recognize a number of these faces, by the way. The value adders, the launchers, and finally, the billionaires. And time runs down the page here. It took some 25 years, 30 years, before people were making money on this thing called the internet. There was a kind of phase change that occurred between the early work, the design, the engineering, and finally, the commercialization. I want to talk about that. So an interesting comment was, I just showed you a picture of dozens of names and people you know whose contributions were important. But here's a more important comment. The internet would have emerged if none of those people, none of us had been born. The concept was in the air. Think again of Tesla's commentary, just awaiting for the technology to catch up to the vision. So there are no key people that had to be born to make this happen. It was going to come. And all the people on this call, all those in the past and the future, have and will continue to contribute to it. But there's an important observation about what was the magic of that period that allowed things to happen for the technology to catch up. And it was basically due to an enlightened funding culture that ARPA was providing. And the culture was the following. They would reach out to the research community and find a great researcher, a well-known researcher, and they would fund her with a lot of money for a long period of time and encourage them to go for high-risk, high-payoff projects, moonshots, if you will. Failure was okay, but don't let that discourage you. And by the way, we're not going to get in your way. You do it as you like in the domain in which you are equipped and competent. Now, what better opportunity to do great research than unfettered, strongly supported, failure is okay, surrounded by people in a similar culture. And of course, what happened, once that money was given to principal investigators at universities, what did they do with the money? They took that money and they funded graduate students, many of whom are at this meeting today. And how was it done? Well, we would go to a graduate student and say, look, there's a following kind of problem. Go figure out how to solve it. I'm not going to tell you. Do it yourself. Basically, form groups with your colleagues if you want, discuss it, invent, try, shoot high. We're not going to bother you. You've got plenty of funding, go do it. Well, that was indeed an enlightened and a golden era out of which came some unbelievable technologies, not only networking, but time sharing, graphics, high performance computing, chip technology, artificial intelligence, on and on and on in that environment. An environment which for a period disappeared and is very slowly coming back with constraints and not nearly the richness of that early environment. So what was the culture that would characterize that period? One in which we were ethical, we trusted each other, it was open, free, shared. We didn't have any patents, we didn't have any private ownership. It was all a community-driven effort in the open, with anything goes, try it, you won't be shamed, just go for it. Now, growing the internet from that period on, when it was first deployed in 1969, we were young engineers, we didn't know any better. In fact, we were nerds. So we launched an effort to create a new technology to benefit the world. That was our goal, a tough new challenge which had value. It was run by us scientists, not by commercial corporate CEOs. We had a model, we had analyzed it, so we knew how the system should behave, but we also knew that the things we didn't know, so we knew how to experiment and measure and stress this thing, much as we just heard in the opening session this morning. Measure it, deploy it, measure it, fix it, stress it, etc. So the growth of the internet, from 1969, its origin, to 1988, it grew rapidly, friendly, broadly, until something happened in 1988. Robert Morris unleashed the first internet worm. And we said, ouch, that's a pain in the neck. And we said, oh, well, it's an aberration. It's probably a mild, unimportant event. What a mistake. That was a harbinger of the dark side of the internet beginning to appear. From 1988 to 1994, we continued. The dot-com came online. We upgraded the backbone to the gigabit speed, thanks not in small part to Vice President Al Gore. The web became a household presence, and some of these larger companies, to be large companies, began to appear. And then in 1994, two lawyers on the internet introduced spam. The first broad-based, mass-deployed spam message occurred. And I don't know how many of you have ever seen the first spam message, but there it is. And basically, it was launched on April 12th, 1994. They were announcing there's a green card lottery coming up in the government, and if you hire us and pay us, we'll help you get into the lottery. These guys were advertising on our research network, our engineering network. That was not allowed. We complained to them. We sent email back to them. We said, shame on you. You can't do that. Cease and desist. How dare you? Well, we sent so much email back to them that we took down their server. An unintended consequence of the first spam message was the first denial of service attack, which is ironic, but it didn't stop. By now, things are out of the bag. And what did it do? Well, the internet, as you know, enables millions of people to be reached by a single user, quickly, easily, at no cost, anonymously. Well, that basically is a perfect formula for enabling the dark side. And indeed, it was just around that time, in 1994, that the dark side began to appear with all of these negative quantities. Invasion of privacy, worms, viruses, denial of service, destruction of property, ransomware, identity theft, fraud, fake news, and a lot more, as we've seen since that period. So what happened to this internet that I knew, that we researchers and engineers were developing and refining for 25 years and curating? We had 25 years to curate it and engineer it. We had a dream of a shared technology, a major scientific advancement, a creation of a miraculous research network with boundless computing magnificence. And what did it do? It became a tool for buying detergent. Well, this genie was now out of the bag. So when did we go wrong? It was in the early 90s, just around the time that spam occurred and the dark side rolled out. And what happened is it reached into the world of the consumer. The consumers took note, and the world, the commercial world, had a huge desire and drive to monetize the internet. Today's net, how did we go from collaboration to now competition, consensus to dissension, from a reliable digital resource to an amplifier of questionable information? How did this medium for sharing turn into a mixed blessing of questionable information and taken over? Well, it was the commercial view of the internet. What do they see the internet as? It's a shopping machine, a gossip chamber, an entertainment channel, a social club, and mostly it's a place to make money. Meanwhile, we've gone from nuisance to dangerous and people who've been attacking us. Hackers at all have always been a nasty nuisance. When they were appearing in the early 90s and on, my thought was, well, the internet is going through its teenage years and it's behaving like a teenager. It's disobedient. Well, it's gone beyond that now. We have dangerous players appearing. Nation states with denial of service attacks, botnets, using artificial intelligence and machine learning in serious ways. Organized crime, international money laundering, and extremists. Everybody has a voice on the internet. So who do you listen to? The ones with the loudest voices. And at the extremes of the spectrum, the extremists are making a lot of noise, and they're being heard, and they're having influence, significant influence. So I want to take you back to the very first banquet lecture at the very first MedComNet meeting. It was in Sardinia, as I told you, September 2002, and see what was going on at that time. Well, notice the title. It's nomadic computing. That was a big issue in those days. And I articulated then a vision I had in 1969, which had these components. I was saying that the internet technology will be everywhere, always accessible, always on. Anybody can plug in any device anywhere at any time, and it will be invisible. And so in 2002, I evaluated, have we achieved that vision, that 1969 vision? And the answer is yes and no. We achieved the first three, but no, it was difficult to move around as a nomad and get easily access to the network. And certainly the internet was not invisible in terms of the good human interface. Let me take the judgment right now. Here in 2020, how do we score this? And the answer is right there. We've improved on one of those. Yes, nomadic computing, mobile computing is clearly been succeeding in many ways. You can plug in anywhere, a device anywhere, anytime, any location, any device, but it certainly is still not invisible. Invisible in the sense that the way in which I'm communicating with you by voice, by vision, by haptics, by gestures, the internet is not nearly that easy to use. It's got tiny little keyboards, complicated apps, different protocols, and the Internet of Things, which as we know is emerging, is beginning to resolve that last bullet, but it's not here yet. Another thing that we commented on in 2002 was the fact that the user really doesn't want to understand it. They want to move up the stack, make all of that complexity disappear, namely make it invisible. And we were talking about that as a goal at that time. I also pointed out that if you see how many years it took for technology to reach 50 million people, radio took almost 40 years, TV, 12 years, cable, 10 years, internet, 5 years, Napster, less than a year. Well, if you look at this graph, it suggests that we're going to not asymptote at zero, we're going to go negative. In fact, technologies will, quote, reach 50 million people before they even deploy. And of course, we've seen that over and over again with pre-announcements of technologies and services long before they're available to the public. So this prediction, in fact, has come true, and that's a negative prediction, unfortunately. Another graph that we showed at the time was the following. We broke down the period from 59 up to the year 2000 into basically an early period where there was no technologies and we just had an understanding of the principles. Then we deployed it at 50 kilobits per second. Computer scientists were the users. In the middle years, we saw public networks try to come on. It was difficult for them. Some interneting problems became apparent, and then TCP/IP was deployed in the next couple of years. Science community finally came in to join the computer scientists as NSF deployed megabit networks. And then the explosion in the 90s when we went to gigabit networking. Nomadicity was important. It was beginning to be deployed. And we saw commercial and consumer population come in, which was the turning point in the nature and the texture and the taste of the internet. And at that point, we were looking into the future. The future was now lived 20 years ago. Gigabit, terabit, petabit networks, pervasive wireless networks, we've seen that, last mile deployed to the home. Also for access, broadband access, transparent access, and the users were going to be these nomads running around, smart devices being deployed, and intelligent software agents in the network. Notice, we did not talk about social networks, the thing which has dominated our behavior in the last 20 years. Because as you know, Facebook was founded in 2004, shortly after the 2002 meeting. We see a surprising and significant explosion of social networking and the use of consumerism and monetization of the internet. So continuing, at that time, we already identified some of the people who are still present around, except for Mario, participating in this conference And the point I should have made earlier is that long list of people who put together this conference is composed of many of the same people who put together that very first conference in 2002, who still say that going on at that point and to today. So one of the things I discussed in this meeting in 2002 is also, I gave what was called a brief history of radio. It's really brief. Marconi in 1901 basically launched the radio wave across the Atlantic. It was a proof of concept. It wasn't too many years later before the world was deployed with radio, and that's the end of the history of radio. Then we have the history of packet radio. Packet radio in the 1970s was an area that was heavily funded and researched by the ARPA community. And the kind of deployment, this is a homely little graph of what was going on. You notice what was happening. The size of the packet radios, 250 cubic inches, 25 watts, and 25 pounds. Basically unusable for deploying in a big way. Well, in 1990s, ARPA again revisited packet radio, again funded its research and deployment. The picture was the same, but the technology had seriously advanced. We made a factor of 25 improvements in all of those dimensions. 10 cubic inches, 1 watt, and 1 pound. So here we are, after that 2002 picture. What are we doing in 2020? What can we say? Well, guess what? The picture is the same. The technology has improved, but we've only improved by a factor of 2. The thing we have improved dramatically, however, is to provide significantly more capability, services, and technology in these devices. And here you all are looking at mobile devices and wireless and cellular systems and trying to deploy and improve them. So a very important domain. 2 years later, I gave a talk again at the third meeting in Bodrum, in Turkey, and the title was Rules of Engagement and a Vision. And I want to talk to you about the internet rules of engagement of which we were aware at this point. I asked the question, what were the unwritten rules of engagement in those early days? And I'm going to give you. The unwritten rules were the following. First, a deep commitment that there would be no centralized control authority. That happened. Secondly, that we researchers were driven by a sense of community. The ideas would be shared freely among all of us. This was not written down as a constitution. There were unwritten, understood rules of engagement. Our gratification would not come by ownership, proprietariness, or money making, but rather the fact that our creative works were being used by others. That was the gratification we sought and achieved. Similarly, one of the technology implementation rules of engagement was we're going to use an end-to-end philosophy. Put a lot of the intelligence at the edge instead of internal to the network. And the last rule of engagement, next to last, was, well, all of us were friendly, well-behaved. There was no need to protect against malicious users. Well, that was a big mistake. In those days, we had a group of users who had a proper sense of etiquette, if you will, the etiquette of cyberspace, and people behaved well. And of course, that didn't survive. This was an era now of open research, everything was shared, no heavy control structure, and most people behaved those rules of engagement, except sadly it was no longer so around the early 2000s, the late 1990s and late 2000s. As I told you, we began to get the dark side of it. So spam and other malicious acts will begin to come up. And we said at that time that the fact that we can reach a lot of people easily and cheaply and anonymously is a kind of curse. It costs nothing to send out all these evil, malicious messages. And we need to find a way to make the spammers were the main malicious users this time, to suffer some economic consequences. We have to basically eliminate the excess. So we're thinking to consider a way to modify, to maybe charge a site from sending excessive email, controlling these spammers. Well, we didn't do that. The spammers were not basically told how to behave. And here we are 20 years later, still dealing with that and still not coming back with a way to control what's going on in the net. That's a challenge we have these days. So what I want to do now is go into a little bit of technology. Just last year, just about a year ago, we had a workshop honoring Mario, and I gave a paper called Keep the Pipe Just Full But No Fuller. I'd like to go dive into that for just a moment. It was published in Ad Hoc Networks, and there's the name of the paper. There were quite a set of wonderful papers published in that journal. So the paper was all about improving TCP. TCP, we know it's a very heavy kind of protocol where you send things from source to destination, and you get an ACK back, and you control how much you flow. And TCP does that flow control for you, using essentially at the early times the work that Van Jacobson did, basically with arithmetic increase and multiplicative decrease. And it looks like this. If you plot the response time versus the throughput of the system, you follow that red line from its left boundary to the right boundary, constantly increasing more throughput until you hit the bandwidth, the bottleneck of the network. And TCP drives you up that red line until it hits the buffer limit. And then it starts to do multiplicative decrease and basically additive increase and moves up and down that vertical red line. Now, sensibly, where would you like to operate? Well, the congestion control was sitting up around the point alpha. It turns out that years ago, in 1970 and 79, I had said, you should be sitting at the point beta, where you're pumping through all you can, but no more, and getting a minimum response time and a maximum throughput. So I wanted to elaborate upon that in this recent paper. The fact is, the behavior really is not that deterministic behavior, but it's more stochastic. It looks like that. And I was able to show that there's a point on that curve you should operate to maximize throughput and minimize delay. And it's at that point beta where a line out of the origin, tangent to the curve. And the intuition is to keep the pipe just full and no fuller. So let's look at that. I define power. Power is the ratio of throughput to normalized response time. You want to maximize power. It's a simple metric, but it has some magnificent properties. And if you plot that on the normalized response time versus the throughput curve, you'll see the equation on the right tells you that it's a straight line relative to any given power function. And so it looks like that. Those are lines of constant power. And there's the power. Power ranges from 0 to 1. Similarly, if you want to look at the average numbering system using Little's result, you get the equation that now the normalized response time is inversely related to the throughput. It's basically hyperbolic, and it looks like that. So those are lines of constant numbering system. And if you put both of those on the same graph, this is the power and the average number for any queuing system. This doesn't say MM1 or MG1, it's any queuing system where you have the throughput and the response time. You'll be able to pick off the power and the numbering system easily from this universal graph. Let's look a little further though. If we choose to invert that normalized response time, we now have a graph which is a 1-by-1 square, and things are now contained in the inverse normalized response time and the throughput. And now those power curves and the average number curves look like this. They basically, the hyperbolas become straight lines and the straight lines become hyperbolas. And this picture is what I call the universal power profile. Any queuing system lives in this space and it's easily found in terms of what it's going to deliver to you. So for example, if you look at the one for MG1, those solid lines are the MG1 curves. And if you maximize power, you lie along that red line. And the interesting thing is that for all MG1, the average number in system at maximum power was when there's on average one person in the system. And that fits so well with your intuition that deterministically you'd like to keep one in the system, nobody in the queue, and the server always busy. So using this metric has allowed us to come full circle and now using these ideas to implement a new basic congestion control system for the internet, which Google is implementing, again, through Van Jacobson and his colleagues, using something called BBR, the bottleneck bandwidth, and the round trip time delay. So enough of that. As a result, I'd like to articulate 5 golden, basically, ideas for research, guidelines, if you will. And here they are. You should ask yourselves as researchers, will my results be remembered 100 years from now? Well, 100 years is a long time. How many things do you remember in the research world, in the engineering world from 100 years ago? There's not many. How about 10 years ago? You shouldn't do work which is going to have a 1-month lifetime and then disappear from interest. Pick important problems. Don't fall in love with your model. Find out ways to approximate it, to change it. Beware of mindless simulation. I feel that computers these days are basically the worst enemy of critical thinking. It's too easy to simulate. I give a student a problem to solve. They'll set it up in a simulation, come back with a curve of y versus x and say, here's the way it behaves. And say, oh, well, why does that portion look like a straight line? And what does the slope mean? What about the intercept? What about the asymptote? What if I double the number of users? What will happen? And the answer from the student, unfortunately, often is, well, I'll simulate it again. And I say, you have no understanding. You don't understand your own results. You have no intuition. So go back and gain that intuition. And that's the job of faculty, to build that curiosity, that intuition, that exploring things and extending one's results. So the paradigm of research is the following, as you know. You create a model, you analyze it, you optimize it, you understand it, you implement it, and you test it. And it's important to understand it, a step often missed by too many researchers. And then you repeat and you iterate that over and over again until you get the results you like. So today's internet, it's adapted very well to the pandemic crisis we have right now. Basically, access to the home had reasonably good bandwidth around much of the world, much of the basically developed world, but that capacity was being used idle during the daytime. Well, the pandemic sent us home, and the internet adapted very nicely and was already providing the bandwidth we needed. So we're doing a Zoom or a GoToMeeting during the day and the night. The network is able to adapt. It's extremely flexible, and that's part of the criteria we built in to be adaptable. But we're having, as I said earlier, serious issues of privacy, security, fake news, inequality, ethics, and the exploitation of the consumerism, which has taken the internet in a very negative direction. And some of the things you're seeing here on this list of bad issues is because people are trying to gain power and exploit the monetization of the network. We as a community, this is a message to all of us, we can't ignore our responsibility to those issues. We heard a little bit about security and attacks to the network in the earlier presentation today. All these issues are our responsibility. We have to, first of all, articulate them. Then we have to discuss solutions. Then we have to implement solutions. And basically, we have to train our students, ourselves, and their descendants to deal with this. You have to take an interdisciplinary approach. Have our students take some courses in business, in ethics, in morality, in basically high-level goals, instead of narrowing our focus just to the mathematics and the engineering tools. We have a broader responsibility. And if we don't have a solution now, it's up to us to help develop it with colleagues across the aisle, which means from the humanities, from the business schools, from the biology world, etc. So that basically is one of the messages. So thank you very much. I appreciate your attention.
Thank you very much, Len. Beautiful presentation. Any inspiring content. We have some time for questions. I invite people to write on the chat their question, or just mention on the chat that they want to ask a question, and then we'll pass this around. Meanwhile, I wanted to ask you. Well, I have many questions, but let me start with one. You said that the nice thing about the packet system is that there was a theory before implementation, and so there was a quantitative approach before implementation. You had an idea of what to expect and so on. But then it seems that the over-provisioning approach has taken over, and the current internet, or at least many portions of the internet, don't pay any attention on the amount of resources. People are convinced that the way of solving problems is just throwing bandwidth, throwing buffer, throwing resources at the problem, and by doing this, fixing whatever. Which in some cases is kind of stupid, because by throwing resources, you risk to make things worse. But that's the difficult message to convey. Will there at some point be some more wisdom in the way we are using resources?
Beautiful question, because you mentioned adding buffers. Adding buffers to the internet routers has only caused more problems, because they get filled up, they cause delays, they cause overflow, they cause loss, and then they cause retransmission, all of those negatives. If you look at what I pointed out about the power, the right place to be is before you fill those buffers. And the flow control has to recognize that. Instead of pushing harder and harder until you recognize you're overflowing, you need to come back. So you're quite right. Over-provisioning is a careless way to try to solve the problem. It's got to be done with intelligence and with care. But you know, in the early days of the internet, the original router had enough room to store. It had 12K of storage for the buffering of packets. 12K. One day they doubled it, 24K, and the network crashed. And the reason it crashed was not over provisioning. It was because of they forgot that if they added more storage, they had to find a way to point to the storage. And they were allocating storage before they found pointers, and things are allocated, congested, could never come out of the router. The point is, there are many ways of running into trouble if you over provision, if you add control and add functionality. And one of the answers to your question is the following. You notice I pointed out that, yes, we understood how it should work. But as you said, we're also wise enough to recognize that we didn't understand everything, and we'd have to measure it. It's critical to continually measure our systems and to stress them. You have to try to push them to the outer envelope of their performance profile so you can find out what's wrong and fix it. If you deploy something and wait for it to break, instead of testing it in an environment where you find out where the breakage points are, you're making a mistake. So the engineering has to be done with intelligence, not, as you say, with over-provisioning.
Okay, we have a question by Alberto Abritzer. Do you want to come up with your mic and ask the question yourself?
So I was a student back in 1986, learned all these concepts and tried to apply it to software system. Not that easy. There's still a big gap in terms of the understanding of networking and internet, and specifically with cloud computing, what you just mentioned, the over-provisioning seems to be the issue there instead of the understanding. So what do you think about it?
Well, software has always been a difficult area. In the earlier days of software, I used to point out that software systems will get deployed while they were being written and long before they were debugged. The debugging was in the deployment, which is a little bit late. And in today's internet, you can't afford to do that because you have major crises. The one thing that perhaps provides some sort of comfort is the current research in the blockchain area, where things can be specified and examined as to what their behavior should be. And I'm sure you're well aware that the theoreticians in the computer science field, those in cryptography and concurrency, are spending a lot of time evaluating fault, performance, and attack on a variety of software systems. They're applying it right now to the blockchain implementation. But that kind of thinking is what's needed. And verification of software, as you well know, is extremely difficult. Formal verification. It's still in its early days. But to look at it, and every one of these studies in the blockchain is very difficult, but very precise. It specifies exactly the domain they're going to look at, the assumptions, and then answer questions. Is it live? Is it safe? Is it attackable, etc. So there is some hope.
Thank you.
Talking about blockchain, Farouk has a question about blockchain.
Farouk, let me see your face.
I'm really glad to see you, and as always, enjoyed your talk. You also a lot of perspective on how the field has evolved and how where it might go in the future. So actually, before you started talking about, I also want to salute Maggie. She's around, and we're very happy to honor Mario today. My question was about blockchain. Actually, we're talking about blockchain, and it seems like we are, in one way, we are trying to repeat the decentralized world of internet within the blockchain. And it's taking a lot of time probably to get the usage or more usage of blockchain in the world. How do you see, are we in the same philosophy of the internet, or are we bringing something new as to this decentralized world? And how do you see the future of blockchain in terms of what are the main issues, let's say challenges with blockchain and, let's say, massive utilization?
Well, that's a great point, Farouk. Let me start by answering, by making an observation. We spent this whole presentation about the internet. And I made the point, we had 25 years when we engineers and scientists could curate it and improve it and test it and get it ready for big time. Blockchain has had no time to curate itself. It came out as a cryptocurrency, and immediately monetization began to drive it. And so we see many of the implementations and the architecture running out there without much care and with a lot of greed. Now, to your question, of course, one of the magnificent things about the blockchain construction is this distributed ledger, which has some wonderful properties. But who controls that ledger is really the issue you're raising. And we've seen a variety of flavors of blockchain implementations come out. There are the federated ones, there are centralized ones, there are ones based, in the case of cryptocurrency, on fiat versus virtual currency, and we've seen the permissionless ones. I believe there's an application for all of them. Certainly the financial community is trying very hard to base it on fiat currency, and to centralize it for control, and government as well are trying to own the blockchains that are being used. So there's a move in both directions. I personally like the decentralized ones. I feel they have the ability to grow and deploy, but have many problems. And we've seen many attacks. We're constantly looking into the theory and the mathematics as to whether or not these systems can be corrupted, fraud attacks, and certainly the concurrency attacks. So it's early to say. I have a lot of optimism for blockchain, but it's in the early stages, and we need the strong theoretical thinking to evaluate what does decentralization mean, where nobody's in control, literally nobody, as we tried to do on the internet. But you know, for many years, the internet had a centralized control. It was called the domain name system, ICANN, and in some sense that still exists. So not all centralized control can easily be yielded when people are trying to corrupt it, which is the case in both the internet and blockchain. I don't think I've answered your question. I just added to your worries.
Okay, I don't see other questions on the chat. I take the opportunity to ask one more thing concerning malicious behaviors. Many people are saying these days that we need an entirely new internet architecture to be able to get out of this issue of malicious behavior, to be able to protect the user, to be able to avoid many of the issues that we witness these days. Do you think that's true? Do you think that we really need to start from scratch, which essentially I believe is not doable? Or will we be able to identify meaningful and useful fixes?
Marco, that's a wonderful question. It addresses the last thing I said on my presentation, namely, this is not only an engineering science issue. It's human behavior. It's, fake news, shaming on the net, fraudulent behavior, nation states causing serious trouble. These are not issues that you and I in this community alone can solve. We have to bring in the rest of the community. On the other hand, we have a contribution to make, to talk about some of the dangers, to talk about what's possible from a technology point of view. But we need some of the humanities people to tell us what's possible from an ethical, from a social, from a legislative and legal point of view, and some form of if you will, responsibility and a price paid in some form for malicious behavior. Right now, there's nothing in place. It's all free for all. Laissez-faire, do what you want. If you get caught, you may have a problem. There are no rules. The rules of engagement have not been articulated to address this, and it's got to be done from an interdisciplinary view, not only from the science world you and I live in, because we understand the technology. We're very bad at affecting social behavior.
Okay, we have Edmundo, and Edmundo, please go ahead.
Hi, Len. Thanks. Excellent talk. And my question is a little bit broad. So in the early days of the internet, and still today, I guess, queuing theory played a very major role in the internet design. So in your opinion, AI, how do you see AI applied to the design of the internet, not in the application side, but in terms of getting understanding of the internet design in the future?
Great question. By the way, Edmundo, you spelled queuing without the extra E. You got to put the extra.
That was the keyboard, not the.
Okay. So the answer is yes, there is a role. Basically, you're talking about as machine learning comes in, it's doing things. It's behaving very well in many of the examples we've seen for face recognition, etc. But once you try to put a lot of optimization, be it through machine learning or by handwriting, into a system, optimized systems are wonderful, but they have some serious problems. Optimized systems behave very well in the domain for which they were designed. And if you take them beyond that limit, they'll crash beautifully. They're designed to behave very well and then have a one-horse show. Basically, they collapse all at the same time. Now, machine learning systems, AI systems, neural networks, will basically design systems, but they may not tell you what the boundaries are, besides not telling you what they're doing, which is another serious problem. But I do worry about trying to optimize systems with technologies, again, machine learning, which we don't really understand, which produce good results in some cases, and good results apparently in other cases where we haven't tested them to their limits. So I think the answer is yes, there is a role for machine learning, but behind that, we have to have the capability, be it through machine learning, AI, or this big neural network up here, to figure out how will it behave, why does it behave in this way, what are the boundaries? So the answer is yes, but. And it's a very dangerous game. I'll give you an example. I go way back in time to the 50s and 60s. One of the first AI programs ever developed was a machine that would play checkers. Nat Rochester developed the system. And it would learn in a very rote fashion how to improve its game. And Nat would play with the machine. And one day when he was fooling around with the program, he accidentally changed the algebraic sign of the objective function from plus to minus. The machine was now programmed to lose. And he began to play with it, and he couldn't tell it was trying to lose until the very last move where it gave up, and the grand solution, he captured everything. The point is, in order to do things well, you can't tell what goal the machine is trying to achieve just by observing its behavior, unless you look into the way it's doing it, and machine learning typically doesn't do that. That's a simple example of a disastrous result because he and we don't understand the way these machine learning systems really behave. So proceed with caution.
Okay, wonderful. Thank you very much. Before inviting everybody to come back tomorrow at 4 European time, I want one more remark. When I prepared the program, I wrote on the shoulder of giants as a frame for the presentation of Professor Kleinrock, and he picked that up by telling us about other giants. But I wanted to be very clear for everybody that in our understanding in preparing the program for MedComNet this year, the shoulders are yours, Len. So thank you very much for being with us. Thank you very much for sharing with us so many inspiring ideas. And thank you very much for cooperating in the preparation of this conference.